A brand of television sets produces two models, a $500 model and an $800 model. There is a $200 audio upgrade available for each model. Sales records show the following distribution. So we have price paid for a TV along the rows here, and that could be either $500 or $800. And then the columns, we have the price paid for the audio upgrade, and if they didn't buy it, that would be 0, and if they did, that would be 200. And then we have the associated probabilities. Let's let the random variable x be the price paid for the TV, and let's let y be the price paid for the audio upgrade. So we have x here along the rows, and we have y along the columns. So the question that we want to answer now is, are the random variables x and y independent? Recall that in order for us to show independence, we have to show that for all possible values of x and y, the probability that x takes on some value given y takes on some value is just equal to the probability that x takes on some value. So first, let's look at some probabilities. Let's find the probability that x is equal to 500. The probability that x would be equal to 500 would be these two probabilities added together, so 0.25. In other words, in this row, x is 500. The probability that x would be equal to 800 would be the sum of these two, so we have 0.75. And then that makes sense because this gives us a sum of 1. Let's find the probability that y is equal to 0. That probability would be 0.60 when we add those two together. And the probability that y is equal to 200 would be 0.4 when we add those together. And just as we hoped, whether we add the totals of the rows or the totals of the columns together, we get 1.00. Now, in order for us to show independence, we're going to need to find some other probabilities, some conditional probabilities. So now let's calculate all of the conditional probabilities that we would need in order to show independence. We would need to calculate the probability that x is 500 given y is 0, and the probability that x is equal to 500 given y is 200, because that's all that can possibly happen if x is 500. And then the same thing for x is equal to 800 given y is 0, and x is 800 given y is 200. So looking at this first one, the probability that x is 500 given y is 0, the probability that y is equal to 0 is 0.6. And that's all we care about in this case because we're given that event has happened, that y is 0. Well, the probability that x is 500 given y is 0 would be 0.15 divided by 0.60. Which would reduce to 0.25. And then the thing that we see there is that that is equal to the probability that x is 500. So for at least one case, we have shown that these two probabilities are the same. Now let's move on to the next. The probability that x is 500 given y is 200 would be 0.1 divided by 0.4. Which is also 0.25, and again is equal to the probability that x is 500. Okay, let's look at the probability that x is 800 given y is 0. We're going to carry this out because so far each of these categories is satisfying that criteria for independence. If any one of them violated that criteria, there would be no point in carrying on just to answer the question, are the events independent? But since they are equal, we're going to carry on, and if we find this for each case, then we will have shown independence. The probability that x is 800 given y is 0, again we're looking at the first column, and we would have 0.45 divided by 0.60, which would reduce to 0.75, which is equal to the probability that x is 800. Again, we're seeing our criteria satisfied, so we carry on to the last one. The probability that x is 800 given y is 200 would be 0.3 divided by 0.4, which again is 0.75, which is equal to the probability that x is 800. So each of these criteria are met, and so we can state that the random variables x and y are independent.